Hi everyone, and welcome to this video on finding the nth term of a quadratic sequence. I'm going to go through step by step the method. Let's get started. The first thing to do is recognize a quadratic sequence. So what is it? A quadratic sequence is one where the difference between the terms isn't constant, but the second difference is. This means that when we find the first difference between terms, they change. But when we find the differences of those differences, they stay the same. So let's have a look at this first example. We've got this here. The first term is 3, second 7, 13, 21, 31. And let's have a look at the differences between them. Between 7 and 3, we've got a difference of 4. Okay. 7 to 13 is a difference of 6. Between 13 and 21, we've got a difference of 8. And between 21 and 31, we've got a difference of 10. Now that's the first difference. As we can see, they're all different: 4, 6, 8, 10. But we find the second difference. So the difference between 4 and 6 is plus 2. 6 to 8 plus 2. 8 to 10 plus 2. And that's the second difference. Now, because this second difference is constant at 2, we know it's a quadratic sequence. And it's going to follow the form an squared plus bn plus c. And what we found first, because we've got this plus 2, we've effectively found what the first coefficient is, a. We have to have this number. We have 2, which would be 1. So 2 divided by 2 was 1, and that equals a. So we know that our first term is just n squared, 1n squared, like that. So we've got the quadratic part. We now need to know this bit. And so what we need to do is take away the n squared part from this, and we'll be left with the linear part. So let's have a go. We're going to put down the original sequence. And I put down the n squared part. And this is for each one. So this is term 1. So we go 1n squared is 1. 2 squared is 4. 3 squared 9. 4 squared 16. And 5 squared 25. And now what we do is we take these terms away from the ones above. So 1 from 3, we've got 2. There we've got 3. 9 from 13, 4. 16, 5, and 6. So now this is our linear sequence, this bit, which corresponds to this bn plus c. So what we now do is find the difference between these. 2 to 3 is 1, 1, 1, 1. So we know we've got this, we found the value of b, so we've got n. So if we put the 1 in, first term where n is, we get 1. But our term here is 2, so we have to add 1 to it. I'll check that works for this up here. Let's check the fifth term, which in this case is 6. Fifth term, just 5 for the n, plus 1, 6, so it works. Then we have to add on this n plus 1 part. Let's put it up there. So this one is n squared plus n plus 1. Done. Okay, the first difference. 6 to 15, 9. 15 to 28 is 13. 28 to 45, 17. 45 to 66 is 21. So that's the first difference. Now we find the second difference. 9 to 13 is 4. 13 to 17 is 4. And 17 to 21 is 4. So that's our second difference. So it's a difference of 4. So we take that 4 and divide it by 2, which equals 2. So we know that our term is going to be in 2n squared. We now put down these values again, and we put in the 2n squared underneath it. So for the first term, squared is 1 times 2 is 2. 2 2s are 4 times 2 is 8. 3 3s 9, 18. 4 4 16 times 2 is 32. And 5 5 25 times 2 is 50. And now we take those away. I like to show it like this. And we're going to minus. So 2 from 6, 4. 8 from 15 is going to be 7. 18 from 28, 10. 32 from 45, 13. 50 from 66, 16. We've taken off the n squared part, the quadratic part. We're now back to a linear sequence. We now find the difference between these numbers. 4 to 7 is 3. 7 to 10 is 3. There we go. Constant. So we're back to a linear sequence. Okay, so this part's going to be 3n. Now, we had a 4 there. So if we put the first term in, 1, where n is, 1 times 3 is 3, but we have to make it 4, so we add 1 on. So our whole thing is going to be 2n squared plus 3n plus 1. That is our answer. Let's check it for the fifth term to see if it works. Right, we put 5 in. 5 5s are 25, times 2 is 50, so this part's 50. 3 times 5 is 15. 50 plus 15 is 65, plus 1, 66. Yes, it works. Let's do another one. We've got 5, 18, 37, 62, 93. Is it a quadratic sequence? If it is, we can put it in this form, find all these coefficients here, a, b, and c, and we will know it's a quadratic sequence if the second difference is constant. So off we go. 5 to 18 is a difference of 13. 18 to 37 is 19. 37 to 62, or 40 to 62 is 22, 25. And then 62 to 93 is going to be 31. Now we look at the second difference. 13 to 19 is a difference of 6. 19 to 25, difference of 6. 25 to 31, difference of 6. So that's proved it's a quadratic sequence. We'll be able to put it in this form. Even if some of these things are 0, we'll still be able to get it in this form in somehow. We take the 6, divide it by 2 equals 3. So we know it's going to be 3n squared. That's our quadratic part. Now we need to know the linear part, which will be this part here. We put down our terms as usual. 5, 18. Put down 3n squared, being this is the first term, second term, third term, fourth term, fifth term. So we put in 1 to start with. 1 squared is 1, times 3 is 3. 2 squared is 4, 4 3s are 12. 3 squared is 9, times 3 is 27. 4 squared is 16, 16 times 3 is 48. And then 5 squared is 25, times 3 is 75. This represents our 3n squared part. We now subtract this from our original terms, which will leave us with this linear part here. 3 from 5, 2. 12 from 18 is 6. 27 from 37 is 10. 48 from 62 is 14. 75 from 93 is 18. We've got a difference of +4. There's our common difference for the linear part. So we now know that we've got 4n to go on. And if we look at our first term of the linear part, which is this, we put in 4 times 1 because this is the first term. 4 ones are 4, but we want to end up with 2. So we have to minus a 2 off of it. So we're going to have -2 as well. We put it all together and we end up with, stick it over here, 3n squared plus 4n minus 2. Done. Well, we've got these two sequences. If you'd like to have a go yourself, then just pause and have a go. Right, so let's have a look. 2 to 6 is 4. 6 to 12, 6. 12 to 28. Oh, this is 20 to 10. So our second difference is 2, 2, 2. So it's +2 each time. So we know we're going to have this. So that's our n squared bit. We'll just put it up here to start with. N squared. We now put our values down again. Put our n squared underneath it. So 1 squared is 1, 4, 3 squared, 9, 16, 25. Take those away. 1 from 2, 1. 4 from 6, 2, 3, 4, 5. Check this difference here. The common difference between these is going to be +1. That determines our n part. So we know we've got +n, just the 1n. And so we now put a value for 1 in. There's nothing to add on or subtract. The c part would be +0. So we can leave that off completely. But we can check it works by putting it into, let's put it into the fifth one. So for the fifth one, the fifth term was 30. 5 squared is 25, plus another 5, 30. So it works. And it will work for all of them. We put it in for the third term. 3 3s are 9, plus 3, 12. Yeah. So that's that one done. Now this one. 5 to 11 is 6. 11 to 19 is 8. 19 to 29 is 10. 29 to 41 is 12. So the second difference is going to be 2. Again, +2, +2. Okay, so that's that. So we know we're going to end up with n squared. Now, put our values down again. 5, 11, 19, 29, 41. Put the n squared values underneath it. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25. Take this away. 1 from 5, 4. 4 from 11 is 7, 10, 13, 16. The difference between them is +3. It is going to be +3n. Now, what's this last bit? For the first term, which is 4, on the linear part, when n is 1, 3 times 1 is 3, but we need 4. So we need to add a 1 on, +1, like that. N squared plus 3n plus 1. We'll try it for the last term. Make sure it fits. 5 squared is 25, plus 3 5s, which is 15, which is 40. Add a 1, 41, so it works. I just want to look at one more example. So we know for a quadratic sequence, we must have a term in n squared. So a can't be 0, because if it was, we'd be back to just the linear sequence like this. And we've seen a case where this one was 0, so this part just disappeared. So we do one more example where b turns out to be 0, and how to recognize that. Okay, we've got this sequence of numbers. We're going to see if it's a quadratic sequence, and to do that, we've got to find out if the second difference is a constant. So let's find the first difference. Minus 1 to 11 is 12. 11 to 31, 20. 31 to 59, 28. 59 to 95, 36. That's the first difference. And let's find the second difference. 12 to 20 is 8. So that's it. 20, yes, 8. 8. That's our second difference. We divide this by 2. Gives us 4n squared. Put down our terms again. This is the first, second, third, fourth, fifth terms. So we put 1 in. 1n squared is 1. Times 4 is 4. And we do that for all of them. 2 squared, 4. Times 4, 16. 9 times 4 is 36. 4, 4, 16 times 4 is 64. And the last one's 25 times 4, which is 100. So that's our 4n squared bit. We subtract that from our original terms. 4 from minus 1, minus 5, and they're all going to be minus 5. That's 16 from 11, minus 5. Yes, minus 5 all the way along. Now they're all minus 5. There's no difference between them. So it's a constant. This is this bit here, C. So our answer is 4n squared. There's no b term, so b is 0, minus 5. Now we could laboriously go through it and prove it. So if I go minus 5, what's the common difference? 0. So that tells us our term for b up here is 0. Okay, so that's worth knowing as well. So we can have c can be 0, b can be 0, but a cannot be 0. Because if a was 0, we'd be back to a linear sequence straight away. Okay, that's it for this week. If you've enjoyed this video and found it useful, then please like, leave a comment, and if you've not yet subscribed, then please subscribe, and I'll see you again soon. Thanks. Good luck with your studies. Bye.